final part of this week's session is called the alternating series estimation theorem. Now this is also an estimation theorem, but it is specifically designed for alternating series only. So this is important. Okay, you cannot use this test for any other series, right? So, and the advantage is the usage is really easy when it comes to alternating series estimations, right? Now remember, we discussed thoroughly about estimations in previous video sessions, right? So when you have a series, we define Rn to be the difference between the real value, the actual value, and the sum of the first n terms. Okay, and here in the alternating series, it says for a series, if it converge, that means if the value is equal to this one, the converging value is equal to S, and if these two conditions are satisfied, and these are the same conditions that we came across when we are discussing the alternating series test, right? And if those same conditions are satisfied by a given series, then this Rn means this one will be less than or equal to Bn plus 1, right? So simply R10 will be less than or equal to the modulus of R10, okay? That will be less than or equal to B11, right? That's just one greater than the number that we are going to consider. So that means if we say S5, that means we are going to add the first 5 terms, right? 1, 2, 3, 4, 5, the first 5 terms, okay? And here when you are adding, you should consider the positive and the negative nature also, right? So by considering those things, when you add the first 5 terms, this addition is represented by S5, and the difference between this one and the actual value will be less than or equal to 1 greater than this thing, right? So here you are not considering the plus or minus nature, you just write down the B value only. But when you are computing Sn, you have to consider all the the complete general term, okay? A3 up to An, okay? Right, let's do an example on this one. And the problem is, find the sum of the series correct to 3 decimal places, right? Okay, so here first of all, by using the alternating series test, we can prove the convergence of this series, right? So we can rewrite the series like this, 1 over n factorial, and this is equal to Bn, okay? And you can see that Bn is a positive sequence where Bn is equal to 1 over n factorial, and Bn plus 1 is equal to 1 over n plus 1 factorial. So definitely the denominator is greater than that of Bn. So Bn plus 1 is less than or equal to Bn, and the second condition is also easily satisfied, we can easily prove that it satisfies, right? What we have is n factorial, so when n goes to a large value, this goes to a large value, therefore the result will be equal to 0, right? Okay, and therefore from the alternating series test, we can say that this series -1 to the power n 1 over n factorial converges. Okay, so that's the first part that we can do. And then to answer this specific instruction, we need to, it's like we know that this series has a finite value, but we don't know that value exactly, so we just need to make an approximation. So we just need to make a approximation so that the difference between these two terms is at least correct to 3 decimal places, right? So let's take something like this. Suppose if the exact value is equal to let's say 1.12345 let's say, just for the sake of explanation, let's say the exact value is equal to this one, right? And suppose if we take a approximation, right, I will name it as A1, right? If our approximation, if we consider it as 1.159873, right, then if we subtract the two values, okay, if we subtract the two values, you can see that you will have a, let's consider this as 1, okay, you will have 0 in the first decimal place, right? So when you subtract the two, you will have 0 in the first decimal place. What is the reason for having 0 in the first decimal place? The reason is, in both S and A1 you had the same number, right? So in other words, it says you have equal values in both approximation as well as in the exact number in the first decimal place. And also if you have 0 for the non-decimal value, that says both this approximation and the exact value has the same quantity in the non-decimal places as well, right? So in other words, in a different way, you can say that this approximation is correct until the first decimal point, right? And now let's take A2 as 1.12 and 2222. Then if you subtract it with S1, you can see that S minus A2 will give you 0.00 something. So here you will have the exact match up to the second decimal place, right? So that's the meaning of this statement, right? We need to find the approximation so that it is at least correct until up to 3 decimal places. Okay, so basically what we need to do is we need to find an error which is at least less than this amount, right? Like for the error, it should at least have 3 zeros for the decimal points, right? After that you can have numbers, right? So this should be our main goal, because that at least 3 decimal places will give you this idea, right? So because now when you say S minus A2, that is basically the remainder that we are considering. Okay, right. And now if we write down the terms of our series, like few terms, you can see that this number, which is the like if we represent this as Bn, this number will be the value for P7. Okay, so this number, now since we have 1 divided by 0 factorial, we will start at 0. It doesn't matter from which number you start, okay, as long as you have this condition, right? And now you can see that B7 is equal to this one. Now for the sequence Bn, we only consider the positive terms only, right? We do not include this negative one that is situated as the coefficient, right? We just consider this positive term only. But if we say An, that will include the negative 1 to the power n as well, right? But here for the hypothesis of alternating series estimation, we only need Bn, right? Here also we need Bn, right? Okay, so what does it say? If the value of Bn, I mean Bn plus 1, if we have this relationship for the value of Bn plus 1, okay, like not this, I mean the alternating series estimation theorem says that we have this relationship for the value of Bn plus 1, right? If the given conditions are satisfied, and we already saw that the given conditions are satisfied for this series, right? So now we know definitely that Bn plus 1 will give you this relationship for the remainder, okay? And you can see by calculating it with the computer or some sort of a calculator, you can see that if you evaluate these numbers, you can see that now even without using calculators you can do that, okay? You can see 5040 is less than 1 over 5000, okay, because 5000 is less than 5040, and this is equal to 0.0002. Now you should be able to do this one without using calculator, okay? The easiest way for you to do is you can just consider this as 1 over 5 times 1 over 1000, right? So 1 over 1000 is, you can just divide 1 over 1000 by 5, okay? So you must be able to do these computations without calculators, right? And that means B7, right? B7 was less than 0.0002. Therefore, from the alternating series estimation theorem, we have this relationship, okay? That means the difference between the real value and the sum up to the first 6 terms will be less than 0.000, I mean 3 zeros and 2. In other words, it says this summation, the error of this summation do not affect the first 3 decimal places, okay, similar to the problem that I explained, right? So that means if we add the first 6 terms, we will get an answer where the error is less than this amount. In other words, you can rephrase the same situation as the sum of the first 6 terms, that is up to this point, will be correct up to first 3 decimal places. Now by using a calculator, if you compute this one, it will be equal to 0.368. okay, so the difference between the actual answer and this value will be less than this amount. In other words, it is accurate up to the first 3 decimal places, right? So we can now if that is enough for our calculations, if that accuracy is enough for our calculation, we can safely write down the answer for the series as this one, right? If this given accuracy is enough. Okay, so that's how we manipulate with alternating series when we need to approximate a certain figure, right? But be careful, this is only true for alternating series. We cannot use it for any other one, any other type of a series, right? So from this one, it will conclude the week 6, and please make sure you complete all the homework and go over the theory quite well, because all this knowledge is required for you to proceed with the theory part that will be done in the next coming weeks. Okay.